Hey everyone, and welcome. Have you ever wondered how scientists can create things with such unbelievable precision? From the medicines that keep us healthy to the futuristic materials in our gadgets? Well, it all boils down to a special kind of recipe, and today we're going to peek inside that recipe book.
So, what's the big secret? Honestly, it's way more familiar than you might think. At its heart, chemistry is a whole lot like cooking. Yeah, really. Chemists are basically master chefs, and they follow a very, very specific recipe book to make everything. And today, we're going to open that book together.
So here's our game plan. We're going to start with the recipe itself, then learn the absolute golden rule for balancing our ingredients. After that, we'll uncover the chemist's secret weapon, their special measuring cup. And finally, we'll see how it all comes together to literally build the world around us. This whole recipe book has a fancy name, Stoichiometry, but by the end of this, you're going to get it. Let's jump in.
All right, let's get right to it. The core idea behind every single chemical creation is just a process of transformation. It's no different from turning flour, eggs, and sugar into a delicious cake. In the world of chemistry, we just call this a chemical reaction.
All that means is you take some starting stuff, called reactants, and you transform them into different new stuff, called products. Seriously, that's it. Reactants are just your ingredients, and products are your finished dish. Simple as that. And check this out. The analogy is a perfect one-to-one match. A chef takes ingredients, and they get a final dish. A chemist takes reactants, in this case hydrogen and oxygen gas, and they get a product, which is water. The chemical equation you see there, that's just the chemist's version of a recipe card. Okay, but there is one golden rule in chemical cooking, a rule you absolutely cannot break. You can't just create ingredients out of thin air, and you can't make them disappear. Every single thing you start with has to be accounted for at the end. This super important idea has an official name, the law of conservation of mass. All it means is that the number of atoms for each element, like carbon or oxygen, has to be exactly the same on both sides of our recipe. What you put in, you must get out. So what does it look like when a recipe is, well, wrong? Take a look at this equation. At first glance, it might seem fine, but if we actually stop and count up all the atoms, we're going to spot a big problem. Okay, let's do the count. The carbons. We've got 2 on the left, 2 on the right. Perfect. The hydrogens, 4 on the left, 4 on the right. We're good. But, look at the oxygen. We start with 4 oxygen atoms in our ingredients, but we somehow end up with 6 in our final dish. That's a huge red flag. It's impossible. You can't just create atoms out of nowhere. This recipe is broken. It's unbalanced. So, how do we fix it? It's actually pretty simple. We just have to adjust the amount of one of our ingredients. See that? We changed the 2 oxygen molecules to 3. Now, we haven't changed what the ingredients are, we just tweaked how much of one we're using. And just like that, look, 6 oxygen atoms on the left and 6 oxygen atoms on the right. Now everything matches. The recipe is perfectly balanced. It follows the fundamental laws of the universe. Now we can cook. Okay, so our balanced recipe tells us the exact number of atoms and molecules we need. But that brings up a pretty big question, right? How in the world do you count out individual atoms? I mean, they're so small you can't see them. And there are trillions upon trillions of them in even the tiniest speck. It really does seem like an impossible problem, doesn't it? But chemists, being very clever people, came up with an absolutely brilliant solution. They basically invented their own special counting unit, a kind of chemist's measuring cup, if you will. And that special unit is called the mole. No, not the furry animal. Think of it like this. When a baker says a dozen, you know they mean 12 of something, right? Well, when a chemist says a mole, they just mean a specific but very, very large number of particles. It's just a convenient word for a number. And just how large is that number? It's that. 602 sectillion, 200 quintillion particles. We call it Avogadro's number. It is a mind-bogglingly huge number, but it's the perfect scale when you're trying to count something as tiny and numerous as atoms. I love this quote because it really puts it into perspective. If you walked into a donut shop and asked for 1 mole of donuts, you wouldn't just get a box. You'd get a mountain of donuts, so massive it would completely dwarf our planet. That's the crazy scale that chemists get to work with every day.
Okay, so let's recap. We've got our balanced recipe, and we've got our special measuring cup, the mole. Now it's time to put them together. This is where we go from just having a recipe on paper to actually predicting what's going to happen in the real world. Here's the key insight. Those numbers out in front in our balanced recipe, they're not just for counting atoms. They're actually mole ratios. So this recipe for burning methane is telling us loud and clear that for every 1 mole of methane we use, we need exactly 2 moles of oxygen to get a perfect, complete reaction. It's the exact proportion we need.
And that one idea unlocks this beautiful, simple 3-step process. Say you know how much of an ingredient you're starting with in grams. Step 1, you convert that mass into moles. Step 2, you use that recipe ratio to figure out how many moles of your product you're going to make. And finally, step 3, you just convert that number back into grams. It's a foolproof workflow chemists use to predict the outcome of basically any reaction.
Now, what's so cool is that this powerful logic, this system of balancing and measuring with moles, it works for all chemical reactions. And just like a chef has different kinds of recipes, for soups or roasts or desserts, chemists also have categories for their recipes. For the most part, you'll run into these 5 main types. You have combination, decomposition, single and double replacement, and combustion reactions. Now, they all do slightly different things, but the fundamental rules we've been talking about, balancing those atoms and using mole ratios, that's the universal language that lets us understand all of them. So, this entire process we've just walked through, learning the recipe, balancing it, and using it to make predictions, that is stoichiometry. And it's not just some abstract math concept. It is the powerful, practical logic that lets us design and build our entire world, one tiny molecule at a time. It's really the ultimate instruction manual for how matter works. So the question isn't just about what scientists and chemists have already built. The really exciting question is, now that you know the basics of how to read the recipe book, what can we create next?